What's up everybody, this is Matt Brown with another IoT hacking video. Today we're taking another look at our tiny security camera. This is made by VStarcam, a Chinese company, and in our last video we performed a firmware extraction. In this video we're going to take that one step further. We're going to get on the device, get a UART console. We're going to then leverage that UART console to get bootloader access on the system. And from there, we're going to do some firmware reverse engineering to find some hard-coded root credentials. So let's first head over to our desk and remind ourselves what this device looks like. So here I have the guts of this camera. On the back side, we can see that flash chip from our previous video. If you haven't watched that yet, I suggest you will go watch that first. So we reattached our flash chip, and now we're more concerned with what is on the other side here. So we're going to take a look at that under the microscope. So let's get that in view. And so right here we have this CPU chip here, the T31 from Engetic is how I think you pronounce that. So I was looking around. I actually did find a data sheet. It wasn't all that useful, but it did tell me something that I wanted to look for on the board. And if you're not blind like I was initially, you've probably already seen it. But let's go and follow this rabbit trail the way I chased it down. So when I find a data sheet like this, if I'm after UART, well, what's the first thing I'm going to do? I'm going to go Control F and I'm going to look for UART. Okay, so we're already getting matches here. It says there are 3 UARTs, UART 0, 1, and 2 on this device. That's helpful. I can hit enter some more, but I can just scroll down to the part that I actually care about, and that's this diagram. I want to know where on the PCB I'm likely to find the UART interface, right? Because for some reason, I didn't see what was staring me right in the face. You probably saw it there in the microscope, but let's ignore that for a minute. So I'm going to zoom in here, and we can see right over here on pin 70 and 71, we can see the RX and TX lines of that UART 0 interface. So that gives us a picture of where on the chip it's going to be located, because we see over here we have pin 1 and it's on this other side where the UART interface, that UART 0 interface is going to live. Well, we head back over to our microscope and we can see that that would be right along this side of the chip. In fact, it would be right around there is where those pins would be. And what do you know, right here on the side of the board, I think when I was looking through this first, I was blind or was just, not thinking clearly, but clearly there are 4 test pads right here, and then they're nicely labeled on the side here. And G, obviously that's going to stand for ground. R is for receive, T is for transmit, N is maybe for like not connected. This might actually be the like a 3.3 volt line. We don't know, we don't care, because what we really care about are the transmit and the receive test pads there. And then obviously we'll need ground to complete our UART connection, but these are very small pads and are going to be hard to connect to. And when you're doing hardware hacking work like this, don't make the job harder than it needs to be. Ground can be found all over the place on the board, and especially on a wireless device, you can find it on wireless antennas, and that's what that is right here. And it's nice and big, and I can connect an alligator clip to it. So I'm only going to have to do this very precise work in connecting to transmit and receive on the UART interface here. And to do that, we're not even going to solder today, because we're going to use our PC Byte probes. So I'm going to slide this over here. And so this PC Byte kit it provides a couple things. So the first very nice thing it provides are these magnetic PCB holders here, which if you can't see that, they retract to clip into the PCB, and that's going to keep it from moving around, which is going to be especially helpful today because I'm going to have to turn this on and off a couple times, and I don't want to bump my probes from connecting when I'm turning this power switch on and off on the camera. So I'm going to go ahead and connect these up here. So there, we're connected to transmit. And with our other probe, we will try to rest it right on the receive pin. Excuse me, the receive test pad. I know you can't see that very well, but they are connected. Now, what are those probes connected to on the other side? Well, they're connected to this. This is obviously not the one they're connected to. This is a different one, but this is a USB to 3.3 volt UART cable. Oh, yes, and we do need to also connect up this alligator clip that, like I mentioned, that's connected to ground. So those are the three things we need to connect to on the board: transmit, receive, and ground. And then we can come over to our computer here, and we can launch PicoCom. So this dev TTY USB 0 in Linux, that's what my USB cable shows up as. And okay, it's printing out a bunch of crap to the console. That's fine, because now I'm going to come over here and very carefully turn this system on, and we can see that the Linux system is booting up. So awesome. And then there's even a speaker on this camera, so it's gonna be saying stuff all the time because it's really annoying like that. So now I can hit enter, and there's a login. So there's lots of ways to bypass a login like that, but today we're actually going to go down the route of figuring out what this root password is on this system. Now, there's ways that we could change the password, and there's pros and cons of doing things that way, but in this video we're going to figure out what the current login password that happens to be hard-coded across all of this device type. So let's take a little bit of a look at the bootloader. So first of all, what we're going to do is we're going to get into the bootloader. You might have seen it there. It scrolled by really fast, but this system does use U-boot, and so what we're going to do, let me get my keyboard ready over here, and then I'm going to turn it off, and then we're going to turn it on again, and I'm going to hold down the enter key in time, and now we can see that we've paused the boot process and we've entered this bootloader menu. The bootloader's not locked, it's wide open, and we can, use all these commands. So the thing that I usually care about most with a bootloader are two things. If I haven't already done a chip-off firmware extraction like we did in the first video in this series, then maybe I could use this bootloader menu to dump firmware. Don't need to do that in this case. What I want is a root shell on this system. And so I'm going to type print env. It's going to tell me all the environmental variables that U-boot has. And here we can see that this boot args environmental variable, this is the one that we're going to care about the most. So I'm actually going to copy that, and then let's make a little file that will keep some notes in down here. Okay, so this is the boot args environmental variable. We want to modify this environmental variable because right now it is booting up into the BusyBox provided Linux RC in it. So it's going to start up the system, and it's going to launch the login Linux program, which is going to prompt us for a username and password, right? And so we don't know the username and password, so we can't interact with the shell, right? But what we can do is we can actually have it boot to something completely different. So what we can have it boot to is a shell bin sh. And so what we're going to do here, so all we have to do is get our command ready to run. So set env is the U-boot menu command to set an environmental variable. It's very important to know, and it's advantageous to us, that when you run this, it doesn't persist. There is a separate command that will persist the environment to the flash so that it uses those environmental variables every time it boots. But we don't want to do that because we don't want to potentially, brick the system by putting some really bad U-boot environmental variable in there. So it's actually good in this case, but we just have to be aware of that every time this system boots, if you want to boot back into your little shell here with bin sh, you're going to have to run this command. You're going to have to interrupt the boot every time and run this command. So here we go. We got our command ready. Let's copy it in. All right, and then we can confirm it if we really want to. We can print the environmental variables again, and we can see that we have updated this boot args variable to have our shell. And now we can just run boot. And now we will see it does not drop into that typical boot process. It just drops us into a root shell. And you'd be like, oh great, you have a root shell. This is awesome. Well, not quite, because if we try to run things like mount, it'll say no proc mounts, right? In fact, the proc file system is not populated at all. So I have prepared a set of commands. This took me a little bit of trial and error to figure out what commands I needed to run to get all of this to work. So I'm going to put them all here. I'll paste them down below so you can see what we're going to run. And I'm going to kind of talk through these. So like I said, the first thing I thought is like, okay, I can't even run the mount command to see what mounts there are on the system. So I probably need to populate proc. Okay, now I can see that I have this squashfs. I have the root file system mounted on slash, and it is read-only. Here it says that it's writable, but it's not really. Don't believe that. Now what we're going to do is we're going to populate dev with a temporary file system, and then we're going to run mount-a. So what mount-a is going to do is it's going to look inside of etc fs tab, and it's going to try to set up all of these mounts that you have specified in your fs tab file. So just do mount-a, and there's one of them that fails, and we don't really care about that because what we want to do will work without this. Now what we can do is run a few of these commands here. And the way that I found these commands is they are located in here. So I don't want to run all of this stuff in the normal init process, but there's some stuff up here that is very helpful. So here is how I mount the system partition that I really care about. And that's where we're going to find eventually the password file that we're going to talk a lot about later. But you can see here that it says, set mdev. So this is how I went down the rabbit trail of figuring all this stuff out. All of these steps, it has the end goal of mounting the file system that is writable, right? So this file system, let's go back here. So right now, we already have access to the root file system with this shell. But on most Linux systems, on embedded Linux systems, I should say, the root file system is usually going to be a read-only system. And then all of the data that is unique per device that gets written and overwritten again during the life cycle of that device is going to be in some different partition. And that's what we find on this device. And so I want to mount that. So that's where all these commands came from. So we're going to run these two. And now, if I do this, you can see that there's a bunch of stuff in /dev. So that's a good sign. And that means that this command is going to succeed to mount the system partition. So now we can cd into system, and we've got our file system mounted. We can run mount. We can see that it's mounted. Cool. So inside of this param folder, we can see that there is a file called password. And there's a password hash, or there's a password hash in here, and the username for the root user. So it doesn't say root, but this is effectively the root user because it is user ID 0, which is root on a Linux system. So we have username VStarcam 2017, interesting, and a password hash. This password hash is using a hash method that I'm pretty sure predates Linux. There are some of you old Unix people out there. You can tell me down in the comments where it came from. So it is very old, not secure, shouldn't use it. It is salted though. What's interesting about this is if you're used to modern password hashes where the $signs separate the salt from the actual password hash, you might look at this and be like, oh, maybe it's not salted. It actually is, technically. It's just a 2-character salt. It can be a maximum of 2 characters. So these first 2 characters are the salt, and then the rest of it is the password hash. So we're going to go ahead and we're going to copy this into our notes for later, because this is important. So what we want to do is we want to crack this, we want to figure out what the plain text password for this user is. So there's a number of things we could do. We could just take this password hash and we could start brute forcing it. And I did that against a lot of word lists that are out there. And so what I'm going to do is I'm going to take this over here where I have a GPU attached to this VM. So what I'm going to do is I'll just type hash, and it just so for hashcat, which is what we're going to run here, it only wants the password hash. And so we're going to do that, and then let's go to here. So this is the examples on the hashcat page, and so we can look for descrypt, which is this old school hash format that's being used, and it's going to tell us that this is type 1500. This is important because when we want to crack this password, we're going to type hashcat, and then we're going to put that identifier, because that's going to tell hashcat what kind of hash it is. It doesn't do any auto detection. So let's say I want to run it against a whole bunch of dictionaries. So this passwords directory is actually from Daniel Meisler's sec lists. It's the password subfolder in there. And so we're just going to run it against every list in there, okay? So we can do this, and we'll just let this run, but it's not going to crack it. Our password, our root password that we're after is not in any of those lists. So we tried that. What's the next step? Let's do some firmware reverse engineering now, because that is going to get us what we want. So I have the folder here with all of the extracted firmware that we talked about from the last video. So what I'm going to do is I'm going to just grep recursively through everything for a password, right? Because that's where that file lives. It's the password file. And so I want to know, is there any program somewhere that generates that password file? Well, let's see. So we get a bunch of hits, and the one we get that's really interesting is this program called encoder. So and you can see again that it kind of like detected like a bunch of these different JFFS2 file systems, which really they're all the same. So what we're going to do is we're going to grab this path, but we're going to just do the first one. Okay, so there's that file. Let's run the file command. We can see that this is a MIPS binary. executable. Let's run strings on it, and let's grep for password. Okay, that's pretty interesting. Let's grep for that username that we have over here. So let's pop over to my other shell, VStarcam 2017. Okay, this is really interesting. So in this binary are the strings etc password, and it also contains the string somewhere in the binary where it's all of that section of the password file except where the password hash should be. We see %s. So if you're familiar with C programming and format strings, this is very obvious that there's going to be some function, some C function that's going to take in a format string, and it's going to take the password and combine it with this pre-formatted string, and it's going to output that somewhere. And then we can make this assumption, because we've seen another part of the system, that it's probably going to then write it to the password file. So to dig into this deeper, we're going to load this program and analyze it with Ghidra. So if you're not familiar with binary reverse engineering, Ghidra is a tool that was open sourced actually by the NSA. So if you're a little, you got to put your tinfoil hat on when you run this program. But it is pretty cool. Here we go. So we're going to double click that. It says we haven't analyzed this binary yet, so it's going to run a bunch of auto analysis, and we'll just let that do its thing. I apologize because I can increase the font size on my terminals, but I don't know where to begin. I can increase some of the font sizes here, and we'll do that where we can. But we're going to allow this analysis to finish, and then, okay, sure, we'll go to the entry symbol. Okay, so our analysis, that initial analysis, the auto analysis it does is complete. So we're gonna go up to the top. I'm gonna say search for strings. Just hit search. And so this is going to find all the strings inside the binary, kind of like our strings command on the command line. But let's go and look for that etc password string. So I'm going to click that, I'm going to double click it, and then in our main window, it's going to navigate to where that string lives. And so what we can do is we can actually right click that string variable and go to references and say show references to the string. There is one reference in the whole code base to that string. That's interesting. Let's go look at that address where it's referenced. All right, let me move this over so my head's not in the way. Awesome. So here we can see, let's increase font size. All right. So here we can see we've got a function that does fopen on etc password, and it opens it with the WB flag. So if you're familiar with that, B stands for binary mode, so it just means that it can write non-ASCII data, non-text data to the file. And then W stands for write. So it's opening the file with the ability to write to it, which, again, with this whole, we're starting to piece together the puzzle, we're starting to put the puzzle pieces together here, and we see our string, again, that format string that we talked about, which is in a sprintf call. So sprintf is going to take our format string, and it's going to take this value here, and it's going to place it into this spot, and then it's going to save it to this variable, which then gets written to our file descriptor, which is etc password. Okay, so we're starting to see that this function is super critical, and so we are going to want to reverse engineer this function a little bit. So let's do that together. Let me try to get that font as big as I can for you all. All right. So the first thing I want to do is I want to start renaming some of these variables just so as I flow through it and reverse engineer it, it kind of makes sense to me. So all these really not helpful variable names, we can rename them, and then it'll rename them everywhere within the function. And if it's a global, it'll rename it globally, right? So here we're going to call this, all right, we're going to call this password hash. All right, so we can see that our password hash is coming here, and it is being set by the crypt function. Okay, that's really interesting. So the crypt function is a function that I think we can look up in the man pages, actually. Let me try this. Here we go, man crypt. Yes, yes, it's here. Okay, so, well, it might not actually do it. Oh no, Ghidra has the documentation. So Ghidra has this ability, so I can hover over it, and it'll actually tell me, because this is a pretty standard function in some library somewhere. And if I hover over it, we can see that the first parameter is a key. It's the password, right? And then the second parameter is the salt. So that's really helpful. So right here, we're going to call this password, and we're going to call this variable salt. So our salt, very interestingly, comes from this function that takes in this variable that comes from a maybe not that well seeded random variable. This is not a important trail to go down, but I did go down this rabbit trail. Actually, okay, this is going to be a side quest. This is going to be a side quest. If any of you want to tell me why this code acts this way and is probably not a good correct use of srandom and random, these functions, you can tell me in our Discord server or in the comments down below. But I'm gonna show you this. So I'll show it right here. So I've got this example test ran that I just like coded up that is equivalent. This C code is equivalent to what is going on in this function. Again, to generate the salt. We don't really care about the salt. We care about the password, but let's go down this rabbit hole. So it sets up, you know, an integer seed, and then it calls time, right? It's calling time with you know, 0, right? It's so you can probably tell me why this is bad, but this is very reminiscent of a video that was put out there by Joe Grand. Joe Grand has an awesome video on like hacking time. Definitely, like, if you haven't watched that video, just like stop watching this one and go watch that one and then come back, okay? It's really awesome. But this code, it generates a random long, and then the rest of the code generates a 2-character salt based on the randomness of this long here. Well, when I run this program, you'll notice there's a problem, right? Like, it generates the same thing within a close time span. So it's probably the salt to this password hash is probably predictable. And what's worse, what's a million times worse on an embedded device is that an embedded device oftentimes doesn't have like a CMOS battery connected to a clock that can persist time across reboots, which means that when the device first boots up, this might be predictable, right? So this would be a really bad thing if it was generating the password this way randomly. But in this case, it's a salt, and we kind of don't care about that. But side quest for people that are really good at C and security. So let's go back to Ghidra And let's track down how this password is generated. So what we can do also in Ghidra is we can use the highlighting to see where that is. And we instantly see here that, quite interestingly, there is this right here. It's setting password to this, and then there's this other variable below it. So Ghidra is not reverse engineering all of this exactly. It's probably not what the original source code looked like, right? So when we hover over this, we see that the characters that this converts to is 7102. So let's go ahead and come over here and just take some notes. All right. So I have to remember what that was. 7102. All right. 710. There we go. And this other value right here is 2190. 2190. Now, when I saw this, I had some suspicions that this is clearly a hard-coded password of some kind, but that that there's an endianness issue, right? So we could see it like this, or if we write it out the other way, and again, this top variable, this was first, and so we would write this out first. So we would go 2017. That's interesting because the username has 2017 in it. All right, and then the second one, if we type that backwards, it's 0912. All right, so what I did is that, in reality, what I did is I tried all of these. I did that, I did this backwards, so let's, try to type backwards, 7102. I tried all these things, right? And I took all these, and hashcat, you can see that it did not crack all those password lists. It didn't crack it, right? But when we take these candidates right here, and we can create our own little password file. Now we can run that same command. Instead of all those files, we can just run it against our candidates here that we've reverse engineered out of Ghidra. We run it, and it says that it cracked it, and that in fact it was 2017 0912. That is the hard-coded root password on every CB73 camera. So that is pretty cool that we were able to figure that out. So let's go and test out our creds. All right. So, oh yeah, okay. So we're in this like half booted up system, but not really booted up. So what we're going to do, for the sake of safety, I'm going to unmount this file system, and then I'm going to power it off and power it back on. And I'm not going to interrupt the boot this time. And like we said, those U-boot environmental variables were not persistent. So now the camera's fully booted up. It's, it's speaking to me over there out of the speaker. And now let's go ahead and, oh yeah, no, it's not root. It's not root. Okay, that's our password, but yeah, that's our username and our password. And now we have a shell on the fully booted device. We can run some commands. It's really annoying. It prints a bunch of stuff in the console. Practically speaking, the way I'm going to work around that is that we can run, you can see that there's telnet D on here. So if I spin up telnet D and then I'm connected to the network, I can telnet into the device and I won't have all this console stuff spitting into my terminal because it will be a different session. So that is the process of how we're able to go from UART, and with the help of our extracted firmware, use Ghidra to reverse engineer a hard-coded password in an IoT device. Thank you everybody for watching this video. I hope you enjoyed it. Please like, comment, and subscribe. Next video, we're going to take it even further and start to reverse engineer some of the network traffic that is being sent back to the cloud server and test and see what the security of those processes is like. Got nothing else for you. Have a good day.